Okay, this is part 2 of Unit 7C, looking at expected values and the law of large numbers. So this next question that we have find the expected value to the company per policy sold. So for each policy sold, and then if the company sells 10,000 policies, what's the expected profit or loss? And that's going to depend on how much they make per policy or how much they lose per policy. So we have an insurance policy sells for $300 based on past data. 1 out of 100 or 1 in 100 policyholders will file a $10,000 claim. 1 in 250 will file a $25,000 claim, and 1 in 500 will file a $50,000 claim. So to find our expected value, okay, we're going to look at each event and the value of that event times it by its probability. So the first one is $300 is the cost of the policy, and the probability that they get $300 is 1. Every person who has a policy has to pay the $300. And so that's a given. Then we're going to say plus. The next one is they'll have a loss of $10,000, and that happens every 1 in 100, so 1 out of 100. And then plus the next one is a $25,000 loss for every 1 in 250. So that's right here. And then plus a loss of $50,000 for every 1 in 500 policyholders. So if I multiply those together and then add them up, I will get exactly 0. So what this means is that the company will make $0 per policy. So I should say they will expect to make $0 per policy. So they'll be right at the break-even point. So if it's $0 for every policy, then the expected profit would just be $0 times the 10,000 policies that they have sold, which is $0 as well. So in this case, they didn't profit, they didn't lose, they were right at the break-even point, and so their expected profit $0, and $0 is again the expected value per policy. So they're right at that break-even point. Okay, the next one, looking at expected wait time. And in this one we have, suppose you arrive at a bus stop randomly. So all arrival times are equally likely. So whether you arrive right when the bus left or right when it gets there or somewhere in between, it's all the same. The bus arrives regularly every 20 minutes without delay. So say on the hour, 20 minutes past, 40 minutes past the hours, and so forth. What is the expected wait time? Well, so to find the expected wait time, so we're going to again go to our expected value. And first it's definitely going to be helpful to determine or figure out, I should say, kind of break down what these wait times possibly could be. So if you get there right when the bus gets there, we're going to try to simplify this down. Then that means you have a wait time of 0 minutes. If you get there right when it leaves. You could also have a wait time somewhere around 1 minute, 2 minutes, 3, 4, 5, 6, all the way up to you just missed the bus and you have to wait the full 20 minutes. Okay, so again, each of these wait times is equally likely. So we're rounding everything to the nearest minute here. So it turns out that from 0 to 20, there are 21 possibilities. With those 21 possibilities, they each have an equal likely chance. So the probability of 0 is 1 out of 21. The probability of waiting 1 minute is also 1 out of 21, and so forth. So for all of those 21 possibilities, it's a 1 out of 21 possibility of waiting. Whether it's 0 minutes, 5 minutes, 10 minutes, they all have the equal probability. So the expected value is going to be 0 minutes times the probability of 1 out of 21, plus 1 minute with the probability of 1 out of 21, plus 2 minutes, 1 out of 21 probability, plus all the way up until you get to 19 minutes of wait time with a probability of 1 out of 21, and 20 times the probability of 1 out of 21. Now, they all have the same probability, so mathematically speaking, we can factor out that 1 out of 21, and we can factor from each portion, because every portion has that same factor timesing by 1/21. So then it would be 121 times the sum of 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up until plus 19 plus 20. Okay, so you'd add all of those up and then times it by 1/21, and it turns out that you would get 10. So the expected wait time for you is 10 minutes. I'm sorry, I'm not sure why we're blurry down here. Might have to reset my iPad. But again, that's your expected wait time on your, when it comes to this bus. So again, everything, the key here is that everything has an equally likely chance or of occurring, all 21 possibilities. So I'm going to pause the video and see if I can fix my iPad here so it's not so blurry. Okay, iPad is back to life. Next we're going to look at what's called the gambler's fallacy. And it's this mistaken belief that a streak of bad luck makes a person, quote, due for a streak of good luck, or that a streak of good luck will continue. So here's a look at streaks. We talked about it a little bit earlier. But when we look at another aspect of the gambler's fallacy, it involves expectations about these streaks. So suppose you toss a coin 6 times and you get 6 heads. Then you toss it 6 more times and you see the following outcome here: heads, tails, tails, heads, tails, heads. Most people would say that the latter outcome is natural, while the streak is surprising. However, both outcomes are equally likely. Because the total number of possible outcomes for 6 coins is 64. Heads or tails on the first, the second, the third, the fourth. So you take 2, raise it to the 6th power, and we get 64. So each individual outcome has a probability of 1/64. So the probability of getting the 3 or 6 heads in a row has the same probability of getting a heads, tails, tails, heads, tails, heads. They all are equally likely. Also, suppose that you just tossed the 6 heads and had to bet on the outcome of the next toss. You might think that given the run of heads, a tail is due on the next toss. However, the probability of a head or tail on the next toss is still 0.5. The coin doesn't remember what happened in the past. And so this idea that something is due, or there's a streak going, the luck should continue, or the luck's going to run out, or whatever, that is a huge fallacy when it comes to random probabilities. So let's take a look at a question that looks at the gambler's fallacy using dice. So I suppose you roll a dice with the following rules. You win $1 if the die comes up even, and you lose $1 if it's odd. So with you're looking at rolling dice, the probability of getting an even is exactly the same as the probability of getting an odd, which is 1/2 or 0.5, because there are 3 evens, 3 odds out of 6. So let's suppose that you get 45 even numbers in the first 100 rolls. So you roll out 45 even, so you win $45, but then that means you lost 55. So you gained 45, but you lost 55. So that would be a loss of $10. So -10 or a loss of 10 on the first part there. So 45% were even, 55% were odd. That's close to our 50%, but not quite there. Now, on the second 100 rolls, your luck improves and you roll 47 even numbers. Okay, how much money have you won or lost in the total 200 rolls? So we're looking at these 100 rolls plus these 100 rolls. Well, so again, 47 out of the 100 were even, so you won $47, but then the remaining you lost, so you lost 53, so it's a -6. So you have a total loss of $16 at this point. It's over 200, so you've lost 16. Now your luck continues to improve, and you roll 148 even numbers over the next 300 rolls. So how much money have you won or lost over the 500? So again, this 300 is counting towards the 100 or the 200 prior to that. But if we look just at the 148, so 148 were winners, and then the remaining, which is 152, because we had 300 total, that's a loss of $4 on those 300 rolls, which brings your total loss to 20. When I add up, again, I'm just basically adding, loss of 10, loss of 6, loss of 4, and that's where my 20 is coming from. Okay, so then the next one says, how many even numbers would you have to roll in the next 100 rolls to break even? So we're down at this point. We're down by $20, so we need 20 more evens than odds on these last 100. So that would mean you would need 60 evens. Okay. And to get 60 evens, that would mean that 60% of those rolls have got to be an even number, which is not likely. So 60 evens is not likely because, again, the probability is 50 out of 100 or 0.5. So it's not likely over the next 100 that you're going to make up those 20. So in the last part, we want to know what were the percentages of even numbers after 100, 200, and 500 rolls. And then we'll talk about the law of large numbers. So after 100 rolls, 45 out of 100 were evens, which is 0.45. So this is after 100. After 200, okay, now for the 200, you got to look at 45 here and 47 there. So after 200, you got 92 out of 100, 92 evens out of 200, which is 0.46. So 46% after 200. After 500, so we would take 45 plus 47 plus 148 on that, or 92 plus 148 out of 500. And our odds increase even more to 0.48 or 48%. So notice that that the proportion of evens approaches 0.5 as the number of rolls increase. So as we get closer to, or as the law of large numbers is applying here, because the more rolls we have, the closer we get to 0.50. But again, we don't exactly land on 0.50, so we shouldn't expect it to be exactly equal, but we should expect it to approach it as that number increases. So we'll end part 2 right there.